Have you ever stopped to think about the ground beneath your feet? It seems incredibly still and solid.
Yet we live on a planet that's constantly spinning. The Earth is rotating on its axis, completing a full rotation every 24 hours.
So why don't we feel this constant motion? Why aren't we flung off into space?
The answer lies in understanding some basic physics. These principles govern everything in the universe, from the smallest atom to the largest galaxy. Grasping these concepts allows us to decode the secrets of our spinning world. Let's embark on a journey to explore the science behind why we're oblivious to Earth's rotation. To understand why we don't feel the Earth's rotation, we need to delve into the world of physics. Two fundamental concepts are key here: acceleration and velocity.
We often use these terms interchangeably, but in physics, they have distinct meanings. Velocity refers to the speed and direction of an object's motion. Imagine driving a car at a constant speed of 60 miles per hour. Your velocity is 60 mph in a specific direction. Acceleration, however, is the rate of change in velocity. When you hit the accelerator in your car, you're changing your velocity, and thus you're accelerating.
Earth's rotation does involve velocity. This constant motion is why we don't feel a sudden jolt or experience the sensation of movement. Imagine a figure skater gracefully gliding across the ice. When they spin, their arms are often held close to their body. This technique helps them spin faster.
It has to do with something called angular momentum. Angular momentum is a measure of an object's tendency to keep rotating. The Earth, like that figure skater, has a significant amount of angular momentum due to its constant rotation. This rotation is remarkably stable. It's not speeding up or slowing down in any noticeable way. Several factors contribute to this stability. One is the Earth's massive size. Another factor is the lack of significant friction in space. This near-frictionless environment allows our planet to maintain its angular momentum and continue its steady rotation for billions of years.
Now let's consider another important concept: angular velocity. Imagine yourself standing on the equator. You're traveling in a huge circle as the Earth rotates.
Angular velocity is the rate at which you're sweeping through an angle as you move in that circle. Here's the key point. Even though the Earth is rotating at a high speed, its angular velocity is relatively slow. It completes a full 360-degree rotation in 24 hours, which translates to a mere 15 degrees per hour. This slow angular velocity is another reason why we don't sense Earth's rotation.
Section 5. Why we're unaware of the right acceleration, velocity, and our atmospheric blanket. In this section, we delve into the fascinating reasons why we don't feel the Earth's constant motion. We've established that Earth's rotation is remarkably constant with minimal acceleration. This steady rotation is a key factor in why we don't sense the movement.
This constant velocity, coupled with our planet's immense size, makes it difficult for us to perceive the rotation directly. The sheer scale of Earth means that any motion is spread over a vast area, making it imperceptible to us. To illustrate why, think about traveling in an airplane. When you're inside, cruising at a high altitude, the motion is so smooth that you hardly notice it. When the plane is cruising at a constant speed and altitude, you barely feel the motion. The experience is so seamless that you can read, sleep, or even walk around without feeling the speed. It's only during takeoff and landing, when the plane accelerates or decelerates, that you feel the force of the motion. These changes in speed and direction are what make you aware of the movement.
Similarly, we're all passengers on planet Earth, cruising through space at a steady pace. Our journey through the cosmos is so smooth that we don't feel it.
Furthermore, our atmosphere plays a crucial role in masking Earth's rotation. This layer of gases acts as a buffer, reducing any sensation of movement. The air surrounding our planet rotates along with the Earth, much like a giant, invisible blanket. This synchronized movement ensures that we don't feel the Earth's spin. This atmospheric drag further minimizes any sensation of motion we might otherwise feel. The gentle movement of air and clouds is a testament to this invisible force at work, keeping our ride through space smooth and unnoticed.
Section 6. Our earthly frame of reference. It's all relative. Our perception of motion is always relative to our frame of reference.
Imagine yourself standing still on the surface of the Earth. From your perspective, you're not moving. However, someone observing you from space would see you moving along with the Earth as it rotates. Your frame of reference dictates your perception of motion.
To illustrate this further, consider two people on a moving train. If they're both seated facing each other, they perceive each other as stationary. However, an observer standing on the platform sees both individuals moving along with the train. Similarly, we're all moving with the Earth, constantly changing our position in space. Section 7. The moon's pull tides as evidence of rotation. While we don't feel Earth's rotation directly, we can observe its effects indirectly. One of the most compelling pieces of evidence is the existence of tides.
Tides are the rhythmic rise and fall of ocean levels caused by the gravitational pull of the moon and, to a lesser extent, the sun. The moon's gravity exerts a stronger pull on the side of the Earth facing it than on the opposite side. This difference in gravitational force creates bulges of water on both sides of our planet, leading to high tides.
As the Earth rotates, different locations on Earth pass through these tidal bulges, resulting in the cyclical pattern of high and low tides we observe. Section 8. Silent proofs of a spinning Earth, from pendulums to the stars. This section delves into the subtle yet undeniable evidence that our planet is in constant motion, spinning on its axis. Beyond the rhythmic rise and fall of ocean tides, several other natural phenomena provide compelling evidence of Earth's rotation. These include the Coriolis effect, which influences weather patterns and ocean currents.
One fascinating example is the Foucault pendulum, a device that elegantly demonstrates the Earth's rotation through its simple yet profound motion. This simple yet elegant experiment, first demonstrated by French physicist Léon Foucault in 1851, offers a visual and tangible demonstration of Earth's rotation. Foucault's experiment was groundbreaking, providing clear, observable proof of our planet's dynamic nature.
A Foucault pendulum consists of a heavy weight suspended from a long cable, free to swing in any direction. This setup allows the pendulum to move independently of the Earth's rotation. As the pendulum swings back and forth, its plane of oscillation appears to rotate slowly over time. This gradual shift is a direct consequence of the Earth's rotation beneath it.
This apparent rotation is not due to any force acting on the pendulum itself. Instead, it is a result of the Earth rotating beneath the pendulum, creating the illusion of the pendulum's plane of oscillation shifting. Instead, it's caused by the Earth rotating beneath the pendulum. This phenomenon is a powerful illustration of our planet's constant motion.
Another piece of evidence lies in the motion of celestial bodies. The stars, planets, and other celestial objects provide a cosmic dance that reflects the Earth's rotation. As our planet spins, our perspective of the stars changes, making them appear to move across the sky. This apparent motion is a direct result of our vantage point on a rotating Earth, offering a nightly reminder of our planet's perpetual spin. Section 9. The Coriolis effect, Earth's rotation in action. One of the most significant consequences of Earth's rotation is the Coriolis effect. This phenomenon is essential in understanding how our planet's rotation influences various natural processes.
This effect describes the apparent deflection of objects, such as airplanes, winds, missiles, and ocean currents, that are traveling in a straight path relative to Earth's surface. Without the Coriolis effect, these objects would follow a simple straight trajectory, but due to Earth's rotation, their paths are altered. Imagine firing a cannonball northward from the equator. As it moves, it doesn't just travel in a straight line. While the cannonball travels in a straight line, the Earth rotates underneath it. This rotation causes the cannonball's path to change. As a result, the cannonball appears to curve to the right, landing east of its intended target. This apparent deflection is a direct consequence of the Coriolis effect.
This deflection occurs because the Earth's rotational velocity is greatest at the equator and decreases as you move towards the poles. The difference in rotational speed at various latitudes is what causes the Coriolis effect to vary in strength.
The Coriolis effect has a profound impact on weather patterns. It is a key factor in the formation and movement of weather systems. It influences the rotation of large storm systems like hurricanes and typhoons. These massive storms rotate due to the Coriolis effect, which helps to shape their structure and path.
The Coriolis effect also plays a crucial role in the circulation of ocean currents. These currents are vital for distributing heat and nutrients around the globe, impacting marine life and global climate patterns. Section 10. A universe in motion, reflecting on our place. Understanding why we don't feel Earth's rotation allows us to appreciate the vastness and complexity of the universe. The next time you gaze up at the night sky, take a moment to contemplate the intricate dance of celestial objects. Stars, planets, and galaxies are in constant motion, governed by the laws of physics. Our planet's rotation is just one small part of this grand cosmic ballet. By exploring the science behind our spinning world, we gain a deeper understanding of our place in the cosmos. We begin to grasp the interconnectedness of all things and marvel at the wonders that lie beyond our atmosphere. Section 11. Conclusion. The wonder of our spinning world. In conclusion, we don't feel Earth's rotation because of a combination of factors: constant velocity. Earth spins at a steady pace with minimal acceleration, immense size. The sheer size of our planet makes its rotation difficult to perceive directly. Atmospheric drag. The atmosphere rotates along with the Earth, further masking any sensation of motion. Frame of reference. We share the same rotating frame of reference as Earth, making its motion our normal. Let this newfound knowledge spark your curiosity and inspire you to continue exploring the wonders of science and the cosmos.